Okay, welcome to Chapter 4. And this chapter in Peleus is entitled Integrated Optic Waveguides. And much of the chapter is concerned with the dielectric slab. A dielectric is a non-conductor and is in general our transparent material. So we can think of either glass or various types of crystals. Various transparent substances are known as dielectrics because in general they don't conduct electricity. And so this topic is important not only because it addresses the issues of waveguiding in integrated optical devices such as couplers and splitters and wave division, arrayed waveguide grating, wave division multiplexers, but also because it forms the basis for understanding the behavior of fibers and the mode structure and the propagation properties of optical fibers. So we'll start with what's called the dielectric slab, and this is sort of an idealization of a waveguide where we consider an infinite slab where we have, here's the slab, and it's in the vertical, and I'll write N1 is the refractive index of the slab, and on the outside of the slab we have indices N2 and N3. Okay? If N2 is equal to N3, it's called a symmetric slab. For obvious reasons. And if N2 doesn't equal N3, it's called an asymmetric slab. Okay. If we have N1 greater than N2 and N1 also greater than N3, then light will be guided inside this slab. In the slab, light is guided in the slab by total internal reflection. Okay, so what we've seen is that if we have light which is incident upon an interface, say between indices N1 and N2, then if that light ray hits, if N1 is larger than N2, and the light ray hits at sufficiently glancing angle, that is, if the incident angle relative to the normal is large enough, then there will be no refracted ray, in which case all of the light is reflected through what's called total internal reflection. And we can picture that here off to the side by just drawing this picture and saying that here's N2, index N2, here's index N1, which is greater than N2, and we're going to go ahead and draw the normal, and we'll draw the critical angle here, and that's the angle at which the refracted ray went to 90 degrees, as you'll recall. So theta critical in this case is the arc sine of N2 over N1. And all the rays which are incident at an angle of incidence larger than this critical angle, theta c here, and now we have a ray whose angle of incidence is larger than that theta c. Let's just call it theta, and we'll say that theta is greater than theta c. Then that ray will undergo total internal reflection, and there will be no refracted ray. So theta greater than theta c implies TIR. Okay? Well, what's going to happen then, suppose that we've got our waveguide here. Let's now consider the slab. I'll draw it in a horizontal configuration. And I'll draw a ray which is bouncing sort of like this, and we'll assume that the angle of incidence is theta, and that theta is greater than theta c, the critical angle. Then what we're going to have is we're going to have this ray bouncing forever back and forth between these external interfaces. Okay, and let's say that theta is here. If we have the situation where theta is not greater than theta c, so theta greater than theta c again implies total internal reflection. If we have the situation where there is a refracted ray, suppose we go like this and go to a smaller angle of incidence, then what we're going to get is we're going to get some refracted ray at each of these interfaces. Okay? And what will happen is the energy of this ray, which is bouncing back and forth, will decrease very rapidly. Okay? So theta less than theta c implies no TIR, and that energy is lost, so rapid reduction in the intensity of the ray. So this ray dies out very quickly, and this one goes forever. Okay, so those are two important cases to consider. And what we'll do then is we will now consider the symmetric slab. And I'll stop the video here and continue on the next one.